बिस्मिल्लाहिर्रहमानिर्रहीम। कॉमसेट्स इंस्टीट्यूट ऑफ इंफॉर्मेशन टेक्नोलॉजी के वर्चुअल कैंपस की तरफ से आप सबको खुशामदीद। आज हमारा फ्लूइड मैकेनिक्स की सीरीज़ का 22वां लेक्चर है और मैं आपका इंस्ट्रक्टर डॉक्टर फ़ाद मुनीर अब्बासी हूँ। As usual, we'll start with the layout of today's lecture. In this lecture, we'll start with the highlights of previous lecture. पिछले लेक्चर में जो चीज़ें पढ़ी एक दफ़ा उनको समराइज़ करेंगे at the start of this lecture. Then we'll go through the applications of the Bernoulli's equation. आज के लेक्चर में हम Bernoulli's equation की applications plus some word problems जहाँ पे utility पाई जाती है Bernoulli's equation की, किस तरीके से और किन जगहों के ऊपर किस किस्म की flow problems के ऊपर हम Bernoulli's equation को यूज़ करते हैं और किन केसेस के अंदर ये हमारे लिए बेनिफिशियल है, ये चीज़ें आज के लेक्चर में देखेंगे। एप्लीकेशंस प्लस द फैक्ट कि किस तरह उनकी यूटिलाइजेशन होती है हम देखेंगे बाय सॉल्विंग सम वर्ड प्रॉब्लम्स। देन विल गो थ्रू द लिमिटेशंस ऑफ द बर्नौलीज इक्वेशन। बर्नौलीज इक्वेशन की लिमिटेशंस क्या क्या हैं। फॉर इंस्टेंस हम कहाँ तक की डोमेन के अंदर बर्नौलीज इक्वेशन को अप्लाई कर सकते हैं, किस किस्म के फ्लोज के ऊपर बर्नौलीज इक्वेशन को अप्लाई करके हमारे पास जो है मोर रियलिस्टिक रिजल्ट्स मिल सकते हैं, ये हम देखेंगे। और किन किस्म के फ्लोज ऐसे हैं, कौन कौन से फ्लोज ऐसे हैं जहाँ पर बर्नौलीज इक्वेशन को अप्लाई करना हमारे लिए बेनिफिशियल नहीं है या हमें रियलिस्टिक रिजल्ट्स नहीं देगा। ये चीज़ें लिमिटेशंस ऑफ द बर्नौलीज इक्वेशन के अंदर आज हम स्टडी करेंगे। देन विल ब्रीफली गो थ्रू द प्रैक्टिकल एप्लीकेशंस ऑफ द बर्नौलीज इक्वेशन। बर्नौलीज इक्वेशन की प्रैक्टिकल एप्लीकेशंस क्या क्या हैं, कौन कौन से इंस्ट्रूमेंट्स के अंदर इसकी यूटिलाइजेशन हो रही है एंड किस किस तरह से इसकी यूटिलाइजेशन हो रही है, ये आज के लेक्चर में हम स्टडी करेंगे। एंड एट द एंड ऑफ दिस लेक्चर आई विल समराइज very briefly whatever we have done in today's lecture. So all in all, चूँकि हमारा previous lecture जो है वो Bernoulli's equation से related था, हमने उसकी derivation देखी, मुख्तलिफ forms देखी, and at that time as well I told you कि next lecture जो कि आज का lecture है इसके अंदर हम Bernoulli's equation की applications के ऊपर ज़्यादा focus करेंगे। जो थोड़ी सी theory and जो mathematical work हमने उसकी derivation के दौरान और integration of the Euler's equation के दौरान किया, वो तो दैट वाज वन थिंग, बट नाउ वी आर कंसर्न विद द एप्लीकेशंस कि किस तरीके से हम बर्नौलीज इक्वेशन को यूटिलाइज करते हैं टू सॉल्व सर्टेन फ्लूइड मैकेनिक्स प्रॉब्लम्स। ये आज के लेक्चर का लुबे-लुबाब है। सो प्रीवियसली वी स्टडीड अबाउट द बर्नौलीज इक्वेशन। ऑब्वियसली हमने बर्नौलीज इक्वेशन को देखा एंड वी जस्ट make the integration of the Euler's equation of motion along a streamline in a rotational flow field। सबसे पहले Euler's equation of motion को हमने integrate किया about a streamline in a rotational flow field and then we integrated the Euler's equation of motion in an arbitrary direction in an irrotational flow field। दोनों केसेस के अंदर हमने देखा कि बर्नौली इक्वेशन कि क्या फॉर्म बनती है और बर्नौलीज इक्वेशन का जो कांस्टेंट है, जो बर्नौलीज कांस्टेंट जिसको हमने कहा था, उसकी क्या खासियत है। जो रोटेशनल फ्लो फील्ड के लिए था, अगर आप उसको रिकॉल करें तो द कांस्टेंट और द बर्नौलीज कांस्टेंट दैट अपीयर्ड इन दैट केस वेरिड फ्रॉम वन स्ट्रीम लाइन टू अनदर बट इट रिमेन्ड कांस्टेंट फॉर अ पर्टिकुलर स्ट्रीम लाइन, whereas the integration which appeared in the irrotational for the case of irrotational flow field that was constant throughout the flow field। So Bernoulli's equation को हमने previous lecture के अंदर analyze भी किया था and we saw that किस तरह हर term की जो dimension है वो length की dimension बनती है and we named it as heads, different heads like pressure head, elevation head and kinematic head and then the total head। and at that time I also told you कि ये energy balance equation भी कहलाएगी as we integrate the Euler's equation of motion। now एक और चीज़ जो बहुत important, मैं previous lecture में भी throughout the derivation of the Bernoulli's equation continuously इसका जिक्र करता रहा कि बेसिकली ये तीन टर्म्स के दरमियान ऐसा रिलेशनशिप है जो हमें ये बताता है कि अगर एक टर्म के अंदर कोई ना कोई चेंजिंग है तो एटलीस्ट एक और टर्म के अंदर वेरिएशन ज़रूर आएगी। फॉर इंस्टेंस आई टोल्ड यू कि अगर प्रेशर के अंदर वेरिएशन है तो देयर मस्ट बी अ वेरिएशन इन द वेलोसिटी और द एलिवेशन और बोथ। सो बेसिकली ये इस तरीके से लिंक अप होती हैं चीज़ें कि एक क्वांटिटी के अंदर, एक वेरिएबल के अंदर चेंज बाकी दो को भी डिस्टर्ब कर सकती है. सो इट वाज लाइक दैट सॉर्ट ऑफ अ थिंग. आज इन्हीं चीज़ों को लेके आगे चलते हुए हम एप्लीकेशंस की तरफ जाएंगे, प्रैक्टिकल एप्लीकेशंस की तरफ, कि हाउ वी अप्लाई द बर्नौलीज इक्वेशन टू सॉल्व सर्टेन प्रॉब्लम्स ऑफ फ्लूइड मैकेनिक्स. As far as the applications of the Bernoulli's equation are concerned, सबसे पहले we'll start with the flow of a liquid from a large tank. हमारे घरों में, ऑफिसेज में, अपार्टमेंट्स के अंदर लार्ज टैंक्स ऑफ वाटर, जिनके अंदर अमूमन वाटर स्टोर किया जाता है और फिर उससे पूरे घर को या पूरी से बिल्डिंग को वाटर सप्लाई किया जाता है. उस वाटर टैंक से वाटर का फ्लो होना also can be analyzed making use of the Bernoulli's equation. Take for instance, consider the large tank as shown in this figure. यहाँ पे एक टैंक, वाटर टैंक अगर आप इसको कंसिडर करें और इसको क्लोजली ऑब्जर्व करें तो इसके अंदर वाटर लेवल एक मखसूस हाइट पे है विद इन दिस टैंक, जिसको हमने 0.1 का नाम दिया है. एज यू कैन सी हियर इट इज. इस पॉइंट की हाइट फ्रॉम द बॉटम ऑफ द टैंक इज नेम्ड एज Z1, whereas the pressure at this point is considered as P1 here. Likewise, जो कि flow out है या outway है of this tank, which is obviously most of the time and for these type of tanks is located at the bottom of the tank. So इस location को हमने 0.2 का नाम दिया and यहाँ पे जो height है from the center of this way out to bottom we have named it as Z2 here, and obviously the remaining height or the difference of two heights is given as H here. Now if we are to measure the velocity or the pressure or the elevation difference between these 2 points, we can use the Bernoulli's equation for this case. Well, through this tank a liquid is being discharged into open atmosphere. If the energy losses within the tank and the short length of the pipe are negligible, then Bernoulli's equation for points 1 and 2 in the control volume can be written as. Bernoulli's equation aside, मैं यहाँ उसको दोबारा एक दफ़ा आपके लिए लिख देता हूँ. अगर आप उसको रिकॉल करें तो it was something like that: v square by 2g plus p by rho g plus z is equal to a constant c. So this was the Bernoulli's equation in one of its forms. इसी को हमने यूटिलाइज करते हुए दो पॉइंट्स के ऊपर, जिसको 0.1 और 0.2 कहा था, दोनों के ऊपर हम Bernoulli's इक्वेशन को राइट अप कर सकते हैं. और देखें इसको यूटिलाइज किस तरीके से किया जा रहा है. V1 which is the velocity of the fluid at location 1, P1 is the pressure of the fluid or the water in this case at point 1, and Z1 is the height of location 1 from the bottom or from the datum line. V2 is the velocity of the fluid at the top at the say location 2. P2 is the pressure at location 2 and Z2 is the height of location 2 from the bottom line. Okay, अब देखें बेसिकली हमने इस पॉइंट के ऊपर प्रेशर, वेलोसिटी एंड एलिवेशन को कंपेयर किया और कंप्यूट कर दिया इस पॉइंट के ऊपर प्रेशर, वेलोसिटी एंड एलिवेशन के साथ, मेकिंग यूज ऑफ द Bernoulli's equation. एंड Bernoulli's equation guaranteed that चूंकि ये क्वांटिटी ऑन द होल कांस्टेंट रहेगी, दैट्स वाई दोनों पॉइंट्स के ऊपर इस होल क्वांटिटी की वैल्यू जो है वो सेम रहेगी. नाउ जो मैं बार बार कॉन्टीन्यूसली एक चीज़ रिपीट कर रहा हूँ और कहता जा रहा था इन द प्रीवियस लेक्चर एंड एट द स्टार्ट ऑफ दिस लेक्चर एज वेल, कि एक क्वांटिटी के अंदर चेंज का मतलब है बाकी दो क्वांटिटीज़ के अंदर भी चेंज होगी, तभी ये कांस्टेंट रहेगी. सो फॉर इंस्टेंस अगर वेलोसिटी एट लोकेशन 1 चेंजेस, देन प्रेशर एट लोकेशन 1 और द एलिवेशन एट लोकेशन 1 ऑल्सो चेंजेस. सिमिलरली अगर प्रेशर और एलिवेशन वेरी करते हैं तो वेलोसिटी भी वेरी करेगी, एंड सिर्फ उसी केस के अंदर ये क्वांटिटीज एट लोकेशन 1 एंड लोकेशन 2 विल रिमेन कांस्टेंट. सो अगर इसको थोड़ा सा रीअरेंज करें तो वी कैन सिंपली गेट दैट दिस फॉर्म ऑफ द इक्वेशन, एंड बाय रीअरेंजिंग इट अगेन we get that V2 square is equal to V1 square plus 2p1 minus p2 over rho plus 2 rho g. Now अगर फॉर इंस्टेंस हमें वेलोसिटी एट लोकेशन 1 पता है, हमें प्रेशर डिफरेंस का पता है दोनों पॉइंट्स के ऊपर, और हमें डिफरेंस ऑफ हाइट का पता है दोनों पॉइंट्स के ऊपर, देन वी कैन कैलकुलेट कि किस वेलोसिटी से फ्लूइड विल बी और वाटर विल बी मूविंग आउट ऑफ द पाइप और आउट ऑफ द टैंक. आई मीन टू से कि अगर आप डिस्चार्ज वेलोसिटी फाइंड आउट करना चाहते हैं एट द बॉटम ऑफ द टैंक, तो फिर you can make use of the Bernoulli's equation, and also you should know the velocity at that point and pressure difference and difference in height between the two locations. This will be important in that case. So is tarah, this was a very simple example of a tank. You can generalize it for any sort of a tank, provided the fact that energy losses within the tank and the short length of the pipe are negligible. Well, short length of the pipe, obviously, by short length of the pipe, we mean that this length is negligible. This short length out of the tank is negligible here. Now also this Bernoulli's equation can be applied for liquid flow over a dam or a spillway. अगर आपको कोई डैम या स्पिलवे देखने का इत्तफाक हुआ हो तो you would have noticed कि किस तरीके से जब डैम के स्पिलवेज या उसके जो दरवाजे बंद कर दिए जाते हैं to store the liquid in it, and then when they are opened, then the water flows out of them. तो जिस तरह water flows out of those spillways, you can calculate, or one can calculate the pressure or the velocity or the elevation of the liquid, making use of the Bernoulli's equation. For liquid flow over a dam or spillway, the Bernoulli's equation for an inviscid flow can be applied, provided friction losses for the short reach of flow under consideration are negligible. Obviously, since water is a viscous fluid or a Newtonian fluid, so it will show the viscous effects. But if we can neglect the viscous effects and the frictional losses due to viscous effects, then we can use the Bernoulli's equation, because the Bernoulli's equation is integrated form of the Euler's equation, which is valid only for the inviscid or ideal fluids. Now for the topmost streamline in the control volume, the pressure is atmospheric pressure and therefore constant at each point, and we may write Bernoulli's equation for 2 points 1 and 2 as अगर बॉटम पे और टॉप पे प्रेशर सेम और एटमॉस्फेरिक प्रेशर के इक्वल रख के उन दोनों को इक्वेट किया जाए तो वी कैन सिंपली कैंसल आउट द टर्म्स कंटेनिंग द प्रेशर एंड कंप्यूट द रिमेनिंग टर्म्स विद ईच अदर, लाइक आई हैव डन here in this equation. So simply you can find out the velocity after the water has passed the spillway and the velocity before the water has passed the spillway, provided the fact that you should be knowing about the velocity and elevation at other locations. So अगर आपको किसी एक पॉइंट पे velocity and elevation known है तो आप किसी दूसरे पॉइंट के ऊपर एलिवेशन के पता होने के बाद उसकी वेलोसिटी फ्लूइड की फाइंड आउट कर सकते हैं इन द केस ऑफ अ liquid flowing over a dam or a spillway. The above equation can be used to determine the velocity of the fluid at any one point, provided that the velocity at the other point is known. So simply, if the velocity is known at any other point, you can calculate the velocity at any point, provided the elevation is known to you. और अगर आप इसको थोड़ा सा figuratively analyze करना चाहें तो it will be say like this. Consider this as a spillway and water is flowing over. Say like this. I hope you can see these dotted lines which I am drawing here. So like this, water spills over a dam or a spillway, and if you know this height, say इसको 0.1 कह लें और इसको 0.2 कह लें, and if you know this, and if you know this height, say Z1 and this height as Z2, and you know the pressure because it is directly contact with the atmosphere, so P1 here is the atmospheric pressure here, then you can make use of the velocity here, say V1, and if velocity here is V2, and obviously density and gravity will remain the same for these location because it is water, so you can use the Bernoulli's equation to compute the velocity at location 2. Now अगर किसी भी और पॉइंट के ऊपर से किसी और पॉइंट पे आप velocity find करना चाहते हैं at this location which is not at the surface, say Z3, you can also compute the velocity or the pressure of the fluid at this point making use of the Bernoulli's equation. So this is big advantage of Bernoulli's equation, and you can see next time जब भी आप कभी किसी डैम को विजिट करने का मौका मिले, obviously थोड़ा दूर खड़े होके, तो observe this whenever the spillways are open, that how water flows and how it is very say flowing smoothly before the spillway से पहले ये बड़ा smoothly water flow करेगा, and after that its velocity will increase rapidly. देखेंगे कि जैसे जैसे यहाँ पे स्पिलवे से पहले चूंकि वाटर की हाइट या जो एलिवेशन थी वो ज़्यादा थी, जैसे जैसे एलिवेशन कम हुई है तो ओनली एलिवेशन कम नहीं हुई, साथ साथ इसकी वेलोसिटी ज़रूर इंक्रीज हुई है. सो ऑन द होल द इक्वेशन रिमेन्स कांस्टेंट, और द बर्नौलीज इक्वेशन रिमेन्स कांस्टेंट. अगर वेलोसिटी इंक्रीज हुई है before and after the spillway, this spillway, and so the elevation is also changed, and hopefully or pressure will also vary if you are calculating the pressure within the flow field and not at the surface. So agar surface पे calculate करें तो obviously we have cancelled out the pressure term, because the pressure at the surface will remain to be the atmospheric pressure. Now let's go for an example which concerns with water is flowing through a pipe of 70 millimeter diameter under a gauge pressure of 3.5 kilogram per meter square and with a mean velocity of 1.5 meter per second. Neglecting the friction, determine the total head if the pipe is 7 meters above the bottom line. Now we are provided that water is flowing through a pipe of 70 millimeter diameter. जो pipe का diameter है, that is 70 millimeter, and the gauge pressure is 3.5 kg per meter square. Now this is the pressure which is provided to us, and with a mean velocity of 1.5 meter per second. Neglecting the friction, we have to determine the total head if the pipe is 7 meters above the bottom line. Now let's start and let's see. First thing, make use of the Bernoulli's equation, and you should know that what are the things which we require here. As from Bernoulli's equation को सबसे पहले write down करें and see what we have to find out. P over rho g plus v square over 2g plus z, or the elevation, is equal to h, or a constant. We have to calculate the total head. This is the total head. the pressure head, the kinematic and the elevation head, but we have to calculate the total head. So this h needs to be find out. और इस h को find out करने के लिए क्या चीज़ ज़रूरी है? देखें, हमें elevation का पता होना चाहिए, हमें velocity का पता होना चाहिए, हमें pressure का पता होना चाहिए. This diameter is given to us. We'll see how we are going to use it. We are provided with the pressure here and with a mean velocity of 1.5 meter per second. Then neglecting friction, determine the total head if pipe is 7 meters above the bottom line. So elevation is also provided to us. Now let's start. Name this as equation 1. Since diameter of pipe is 70 millimeter or equal to 7 centimeter. Pressure P is equal to 3.5 kilogram per meter square. चीज़ ज़रूर इन चीज़ों को ज़हन के अंदर रखें that this is in meter square. अगर ये quantity हमें centimeter square के अंदर होती then we had to convert it first in the meter square because other quantities are given, or take for instance this velocity is given in meter per second, so we have to calculate this in this manner. Now velocity v is equal to 1.5 meter per second and the elevation or z is 7 meters. Now again z is known to us, velocity is known to us, pressure is known to us, and the pipe diameter is known to us. Let's see how we utilize this. So from 1 total head is given as h is equal to z plus v square over 2g plus p over rho g. This comes out to be, since z is 7 meter, so 7 meter plus v square over 2g. V square is 1.5 square, because the value of velocity is 1.5, 2 into this is 2, and the value of g, which is 9.81 meter per second, plus p, which is 3.5 kilogram per meter square, over rho g. और अगर rho g की वैल्यू आप सब्स्टिट्यूट करें तो दिस इज 1000 kilogram per meter cube, as rho g is equal to specific gravity and equal to 1000 kilogram per meter cube for water, and g is equal to 9.81 meter per second square. Now simply by adding these terms you can calculate the total head, and I leave it up to you कि आप इसको add up करके द वैल्यू ऑफ टोटल हेड फाइंड आउट कर लें, और यू कैन डू इट विद द हेल्प ऑफ अ कैलकुलेटर. नाउ एक और चीज़ ज़रूर ज़हन में रखें, लाइकवाइज जैसा कि इस सिंपल एग्जांपल के अंदर कहा गया कि यू हैव टू कैलकुलेट द टोटल हेड, आपसे काइनेमेटिक हेड के बारे में भी पूछा जा सकता है, आपसे वेलोसिटी और एलिवेशन हेड के बारे में भी पूछा जा सकता है. सो यू शुड बी फेमिलियर कि हम किस तरीके से चीज़ों को मैनिपुलेट कर सकते हैं और कौन कौन सी चीज़ें इसमें वेरी होंगी और कौन कौन सी चीज़ें हमें चाहिए होंगी. So we first have to calculate those. This was a very simple example to start with, जिसमें I just wanted to make you people familiar कि किस तरीके से इसको workout किया जाएगा. Now let's move to the next example, which states that water is flowing through a tapered pipe having diameters 15 centimeter and 5 centimeter at the larger and smaller ends respectively. Determine the velocity head and the rate of discharge in liters per second at the smaller end if the velocity of water at larger end is 2.5 meter per second. Now we have to determine the velocity head and the rate of discharge in liter per second at the smaller end, provided we are provided with the velocity of water at the larger end. And let's see how we pursue with this example, since it is given to us that diameter at the larger end is 15 centimeter or equal to 0.15 meter. Here it is given that diameter 15 centimeter and 5 centimeter at the larger and smaller ends respectively. So diameter at the larger end is 0.5 meters. Now making use of this, area of the larger end, और इसको A1 का नाम दे देते हैं, is equal to 1/4 pi d1 square. This comes out to be pi/4 into 0.15 whole square, which is equal to 0.01767 meter square. Making use of the calculator, you can verify this value of the area, whether I have written it correctly or not. I leave it up to you to verify this whenever you are going through this lecture again, and name this as 1. Now similarly, diameter of the smaller end is 5 centimeter or equal to 0.05 meter, and area of the smaller end is equal to A/2, A2 से इसको रिप्रेजेंट किया, and pi/4 d2 square, which is the diameter, and it comes out to be equal to 0.00196 meter square. Name this as equation 2 here. Now we have calculated the area of the smaller and the larger ends in this case. Now let's see how we are going to use them. Velocity at the larger end is also given to us. Velocity at the larger end is equal to if the velocity of water at the larger end is 2.5 meter per second. Velocity is given as 2.5 meter per second at the larger end. Now, calculate हमने क्या करना है? Take this into consideration. We have to calculate the discharge. What you mean by discharge? हमने ये concept पहले भी discuss किया, and we are again discussing it, so you should be familiar with it. What is discharge? It is the amount of fluid flowing out of the let's say any pipe or any channel in a unit time. Kitna fluid is flowing, kitna fluid is coming out of a pipe is named as discharge of the pipe. Now at larger end, discharge, उसको Q से नाम दे दें, is equal to A1 and V1. Area through which the liquid is flowing into the velocity. जिस speed से water is flowing out of that area will give us the discharge. जितना उसका area ज़्यादा होगा उतना ज़्यादा fluid will be flowing out of that, and जितनी velocity of the fluid will be higher उतना ज़्यादा उसका discharge होगा. It is similar to say like अगर आप कोई टैप ओपन करें, कोई नल ओपन करें, तो जिस स्पीड से उससे पानी गिरेगा उतना ज़्यादा पानी थोड़े वक्त के अंदर आप हासिल कर सकते हैं. सिमिलरली जितना उस टैप का एरिया उसके फेस का ज़्यादा होगा उतना ज़्यादा फ्लूइड विल बी फ्लोइंग आउट ऑफ इट. सो इट्स अ सिंपल कॉन्सेप्ट, यू शुड बी familiar with it. Now at smaller end, flow or discharge is equal to A to V2. Velocity at that point into area of the smaller end will give us the discharge at the smaller end. Since discharge is continuous, so discharge at the both ends will be equal to each other. A1 V1 is equal to A2 V2, or from here you can write it down that V2 or the velocity at the smaller end is equal to A1 V1 over A2, and we can name this as equation name this velocity as equation 3 and this as equation 4, plus इन दोनों equations को 3a करके लेबल कर दें. अब हमें velocity का relationship पता चल गया because velocity at the smaller end was not provided to us. So we have developed the relation for the velocity at the smaller end making use of the continuity of the discharge, because discharge is continuous. ऐसा नहीं है कि larger end से discharge ज़्यादा है और smaller end से कम हो जाएगा because of the continuity of the discharge. So using 1, 2, 3 and 4 we get now equation 1 और से 3 तक की values जो है equation 4 में put करें. 1 we have calculated the area of the larger end, in equation 2 we have calculated the area of the smaller end, and in equation 3 we have the velocity at the larger end here. So we can calculate the velocity at the smaller end by simply 0.01 0.767 into V1, which is 2.5 meter per second, 2.5 meter per second, over A1, which came out to be 0.00196. And if you calculate it, it will be equal to 22.5 meter per second. And again, verify this by your own self and see whether this value which I have written it is correctly written or not. Now we know the velocity at point 2, जो कि लोकेशन 2 पे और द स्मॉलर एंड के ऊपर हमें वहाँ पे वेलोसिटी पता चल गई. अब दूसरी चीज़ जो हमने कैलकुलेट करनी थी, कीप दैट इन माइंड व्हाट वी हैव टू डू एंड व्हाट वी आर डूइंग. डिटरमिन द वेलोसिटी हेड and the rate of discharge in liter per second at the smaller end. We have to calculate the velocity head at the smaller end as well and rate of discharge at the smaller end. So अभी तक हमने सिर्फ velocity at the smaller end calculate की है, and we will make use of this to calculate the discharge at location 2 or the smaller end. Now using 2 and 5 in 3A, we get Q, or which is discharge at smaller end. Discharge at the smaller end is the product of area of the smaller end plus the velocity at the smaller end. So हमने area भी calculate किया है and हमने velocity at the smaller end भी calculate की है. तो area की value 0.00196 and velocity is into 22.5 meter per second, and it comes out to be 0.0441 meter cube per second, or equal to 44.1 liters per second. So this is the discharge at the smaller end, which we have calculated making use of the area of the smaller end and the velocity at the smaller end. अब दूसरी चीज़, we had to calculate the velocity head here, so we will pursue towards that now. Velocity head, and what is the other name of velocity head? You should be knowing that it is the kinematic head at the smaller end. This is equal to V square over 2G. So, and obviously V2, because we named the velocity at the smaller end as V2. So this is on the whole the velocity head at location 2 or at the smaller end. Simply substitute the values of velocity and gravity in here. The velocity at point 2 or at the smaller end was 22.5 meter per second, so it's 22.5 square plus 2 into 9.81 meter per second square. So the velocity head comes out to be 25.81 meter. So use again verify these values whether what these calculations give. इसी तरह velocity head हमने फाइंड आउट कर लिया. अगर हमें elevation head कहा जाता तो हम elevation head भी इसी तरह फाइंड करते, which simply was equal to z itself or the elevation itself at the location 2 or at the smaller end, plus the fact अगर हमसे pressure head कहा जाता तो हम pressure भी calculate करते making use of this provided the fact कि हमें pressure at location 1 पता होता तो हम pressure at location 2 भी find out कर सकते हैं. So this is how we use the Bernoulli's equation to solve the word problems and calculate different values of different parameters at different locations. Now consider one more example in which the diameter of a pipe changes from 20 centimeter at a section 5 meter above bottom to 5 centimeter at a section 3 meters above bottom. The pressure of water at the first section is 5 kilogram per centimeter square. If the velocity of flow at the first section is 1 meter per second, then determine the intensity of pressure at the second section for water. Rho g is equal to 1 or 1000 kilogram per meter square. So we have written it simply as 1, making use of these quantities. Now we have to determine the intensity of pressure at second location. Okay, हमने pressure at location 2 find करना. What is provided to us? It is given that diameter of a pipe changes from 20 centimeter at a section 5 meter above bottom to 5 centimeter as at a section 3 meters above bottom. देखें, if you feel easy, you can draw the diagram of it even for the understanding. If this is the bottom line, then the statement of the problem tells us that diameter of a pipe, there is a pipe whose diameter is changing from 20 centimeter to 5 centimeters. So take this as 5 meter and take this as 2 3 meters here. So जैसे 5 meter से 3 meter की तरफ हम move करते हैं, the diameter of the pipe changes from 20 centimeter to 5 centimeter here. Now this is the bottom line, plus the pressure at the first section is 5 kilogram per centimeter cube. Now the pressure is provided to us at the first location, and if the velocity at the first section is 1 meter per second, this is the velocity at the first section of the pipe, and we have to calculate the pressure at the second section of the pipe. So consider this geometry. This is air and water is flowing in this pipe like this. So simply एक पाइप है जिसका डायमीटर चेंज हो रहा है 20 सेंटीमीटर और एंड पे इसका डायमीटर है 5 सेंटीमीटर और दोनों एंड्स की जो डिफरेंस ऑफ हाइट है दैट इज 5 मीटर एंड एट द लोअर एंड इज एट 3 मीटर from the bottom line, and we have to calculate the pressure, intensity of the pressure. Now diameter of pipe at section 1 is 20 centimeter. इसको D1 का नाम दें, and it is 20 centimeter, not meters. It is 20 centimeter here, और इसको D1 का नाम दिया. And also if you like, you can mark these sections as section 1 and section 2. Now area of pipe at section 1 is equal to A1, which is pi by 4 d1 का square, this is equal to, comes out to be equal to 100 pi centimeter square. Further, height of section 1 from datum. Datum से section 1 की जो height है, that is 5 meter. Now because the diameter is given in centimeter, either you can convert the diameter into centimeter or you can convert the height above the datum into centimeters. हम centimeter को तो meters में convert कई दफ़ा कर चुके हैं. Let's this time around let me go for the other way around, and let's convert the meters into centimeters so that you should be familiar with both the cases. Now if it is 5 meter, then it becomes 500 centimeter, and name this as, say, Z1. Now diameter of pipe at section 2. Section 2 पे जो diameter है, that is equal to D2, and that is equal to 5 centimeter, and area of pipe at section 2 is A1, and it is equal to, say, pi by 4 D2 square, and this comes out to be equal to 6.25 pi centimeter square. And height of section 2 above datum. Height is given as 3 meter, and name this as Z2, and it is equal to 300 centimeter. Now we are provided with the data whatever we had. Now let's move. We have to calculate what? We have to know the pressure, and pressure at section 1, name it as P1. It is given that it is equal to 5 kilogram per centimeter square. Okay. Per centimeter square, and since अगर इसको हम किलोग्राम पर सेंटीमीटर की बजाय ग्राम पर सेंटीमीटर में रखें तो it becomes 5000 ग्राम पर सेंटीमीटर स्क्वायर. ग्राम में क्यों कन्वर्ट किया किलोग्राम से? बिकॉज वी यूजिंग दिस सेंटीमीटर, सो इट विल बी रादर कन्वीनियंट टू कन्वर्ट इट इनटू ग्राम्स इंस्टेड ऑफ द kilograms. Now velocity at section 1 is V1. It's 1 meter per second or 100 centimeter per second. Let now V2 is equal to the velocity X section 2 and P2 is pressure at section 2 in kilogram per centimeter square. Now we know that the continuity of discharge tells us that A1 V1 is equal to A2 V2. So from here V2 is equal to A1 V1 over A2, which is 100 pi into 100, which is the V1 or the velocity at section 1 given here, over A2, which is here it is A2, not A1, A2, and A2 is equal to 6.25 pi, and it comes out to be equal to 1600 centimeter per second, which is V2 according to our calculation making use of the Bernoulli's equation. So V2 हमने find out कर ली. Now let's move towards the application of the Bernoulli's equation here. Applying Bernoulli's equation for both the ends of pipe, we get Z1 plus V1 square over 2G plus P1 over rho G is equal to Z2 plus V2 square over 2G plus P2 over rho G, and Z1 because it's the height above the bottom of section 1, and it was 500 because it was 5 meter, so it is 500 centimeter plus 100, which was the velocity at section 1, 2 into since G is 9.8 meter per second square, and when you convert it into centimeter per second square, it simply can be written as 981 plus 5000 grams per centimeter into rho G, which is 1 converted into this scale, is equal to 300, the value of Z2 plus V2 we have also calculated. This came out to be 1600 if I'm 1600 square over 2 into 981 plus P2 over rho G, which is 1 again. So simply add up these things and calculate the value of P2. This comes out to be 3.9 kilogram per centimeter square. So ऐसे अगर हमें velocity and pressure की वैल्यू किसी दो लोकेशंस के ऊपर मालूम हो, तो हम किसी तीसरी लोकेशन पे भी वेलोसिटी की वैल्यू फाइंड आउट कर सकते हैं, प्रोवाइडेड हमें हाइट का डिफरेंस दोनों पॉइंट्स का नोन हो. This is how we use the Bernoulli's equation, and this is how we solve these equations to calculate different values of say pressure and velocity and elevation at different locations. But there are certain limitations of the Bernoulli's equation. Take for instance the Bernoulli's theorem or the Bernoulli's equation has been derived on certain assumptions which are rarely possible. Now the Bernoulli's theorem or the Bernoulli's equation has been derived on certain assumptions which are rarely possible. Thus the Bernoulli's theorem has the following limitations. First of it is the Bernoulli's equation has been derived under the assumption that the velocity of every liquid particle across any cross section of a pipe is uniform, but in actual practice it is not. The velocity of a liquid particle in the center of the channel is maximum and gradually decreases towards the walls of the pipe due to the pipe friction. Thus, while using the Bernoulli's equation, only the mean velocity of the fluid should be taken into account. I've been telling you again and again कि जब भी fluid flows through a pipe or a channel, तो pipe के center में fluid की velocity maximum होती है और ये reduce हो जाती है जैसे जैसे we move towards the walls of the pipe. But in Bernoulli's equation, we take the velocity to be uniform at all points, but in reality it is not the case. So whenever we are going through the utilization or application of the Bernoulli's equation, we must take into account the average velocity instead of the overall velocity or the velocity at different locations. Secondly, the Bernoulli's equation has been derived under the assumption that no external force except the gravitational force is acting on the liquid, but in actual practice it is not. There are always some external forces such as pipe friction acting on the liquid. Thus, while using the Bernoulli's equation, all such external forces should be neglected. But if some energy is supplied to or extracted from the flow, the same should be taken into account. Bernoulli's equation की derivation के दौरान I kept telling you that only the gravitational forces are taken into account, but there can be other forces acting on the fluid as well, जो कि हम Bernoulli's equation के अंदर consider नहीं करते. This can also alter the results. For example, pipe friction नहीं करते. For example, कोई external magnetic या electric field का effect जो है वो नहीं discuss करते. So this consideration can alter our results by a great amount. Now the Bernoulli's equation has been derived under the assumption that there is no loss of energy of the liquid particle while flowing, but in actual practice it is rarely so. In a turbulent flow, some kinetic energy is converted into heat energy, and in a viscous flow some energy is lost due to shear stress. Thus, while using Bernoulli's equation, all such losses should be neglected. I told you again at the time of Bernoulli's Bernoulli equations derivation that we neglect all the viscous effects because it is simply the integrated form of the Euler's equation of motion. So we neglect the energy losses due to the viscous forces. हमेशा viscosity की वजह से energy loss होती है, उन तमाम losses को हम neglect कर देते हैं. जैसा कि आपने एक दो examples जो हमने solve की, इनके अंदर भी देखा तो statement के अंदर भी एक चीज़ मौजूद थी that we should neglect the energy losses. So अगर energy losses को neglect करते हैं तो हमारे results में कुछ changing की तवक्को ज़रूर मौजूद है. हर जगह पे हम viscous effects की वजह से energy losses को neglect नहीं कर सकते. So उन cases के अंदर Bernoulli equation will not give us very good results. And so while using the Bernoulli's equation, all such losses should be neglected. If the liquid is flowing in a curved path, the energy due to centrifugal force should also be taken into account. Again, अगर fluid जो है वो किसी curved domain में move कर रहा है तो then there will be centrifugal force as well, and we must take that into account as well. Practical applications of Bernoulli's equation can be seen in the venturimeter, which is an apparatus for finding out the discharge of a liquid flowing in a pipe, in orificemeter, which is used to determine the discharge in a pipe, and the pitot tube, which is an instrument to determine the velocity of flow at the required point in a stream. Now with this I take you towards the summary of today's lecture, And in today's lecture, we went through the applications of the Bernoulli's equation. हमने Bernoulli's equation की application देखी, particularly the flow in a liquid or a water tank and the liquid flow over a spillway of a dam. Then we solved some word problems and made use of the Bernoulli's equation to determine the pressure and velocity at different locations, provided that some of the values of the unknowns or the variables were known to us. तो किसी पॉइंट के ऊपर, किसी एक पॉइंट के ऊपर अगर हमें वेलोसिटी, प्रेशर एंड एलिवेशन पता हो, तो किसी दूसरे पॉइंट के ऊपर we can calculate these provided if some of them are known to us. So and then at the end we went through the practical applications of the Bernoulli's equation, जिसमें कुछ इंस्ट्रूमेंट्स के नाम आपसे शेयर किए, which made use of the Bernoulli's equation to calculate the flow rate and the discharge rate in that. And with this, it's time for today's quote, and make use of the fact, most of the times when I'm teaching in the class, the students are always there and keep asking that we are not very lucky and we have bad luck sort of a thing. So मैं ज़रूर अपने स्टूडेंट्स को एक चीज़ कहता हूँ कि write down this word luck in front of you and analyze it. इसके एक एक लफ्ज़ को एनालाइज करें. इट्स अ कम्बिनेशन ऑफ 4 letters LUCK. No, once there was a philosopher who said that the letter L in the luck stands for the labor, the U for the understanding, the C for the character and K for the knowledge. So labor, अगर आप हार्ड वर्क करें और कंटिन्यूस हार्ड वर्क करें तो यू कैन मेक अप योर ओन लक. एंड यूज फॉर द अंडरस्टैंडिंग, अपने आप को ज़्यादा बेहतर समझें कि आपके एडवांटेजेस क्या हैं, आपके डिसएडवांटेजेस क्या हैं, एंड वर्क ऑन देम एंड कैपिटलाइज ऑन देम. जब तक आप अपनी अंडरस्टैंडिंग नहीं रख पाएंगे, यू विल नेवर बी एबल टू बिकम लकी. एंड सी इज़ फॉर द कैरेक्टर. कैरेक्टर के मतलब तो हमारे लास्ट लेक्चर में भी बात हुई थी. सो इफ़ कैरेक्टर इज़ लॉस्ट, everything is lost. You should take care of that into account. And K is a knowledge. So always go for labor, always go for understanding, always go for character, and always go for knowledge. And at the end of the day you will become lucky. Allah पाक आपको और आपके घर वालों को बहुत सी आसानियाँ दे इंशाल्लाह. till our next lecture, it's Allah Hafiz from my side.